Hello and welcome. So our next presentation and the last one before lunch is we have Antoine Toubhans, who is going to be talking about flexible machine learning experiment tracking system for Python coders with DVC and Streamlit. Let's welcome Antoine with a round of applause.
Hi everybody, thank you for being here. Today I'm going to talk about ML experiment tracking system. A few words about me. My name is Antoine Toubhans. I'm French. I live and work in Paris. I work in a consulting firm called Sicara. And what we do is that we build a tailor-made solution for our clients, AI solutions mostly. I am a data scientist for 5 years now, and I mostly work on computer vision problems. So today I'm going to talk about machine learning engineering. At Sicara, the official job title is data scientist, but actually what we do is more machine learning engineer because we do data science, we read research paper, we implement models, we run experiments, but we also build what is around. We build APIs, we integrate models in mobile app or stuff like that. So it's in between data science and software engineering, and in software engineering we have a lot of tools. I mean, the software engineering is very mature, and you can leverage on existing best tools and best practices. So on the other hand, machine learning engineering is more than just software engineering. There is a lot of things that you need to do. You need to track the data alongside the code. It's more an exploratory work. You have to try and test things. And as you train models, you need tools to investigate them, to touch them, to see how it works. So today I'm going to talk about ML experiment tracking system. In most machine learning projects, you have this loop when somehow you have some data and you want to try some models, so you train your model. Then you evaluate it, and it provides you with feedbacks. So either you modify the data or the model, you change hyperparameters or things like that, and you do it again. And for these reasons, you need an experiment tracking system that allows you to track your experiments. So you want to have a record of which data did you use, which code, which parameters. You want to be able to compare experiments. And as the project is going on, you are going to have more and more experiments, so you need to organize them so that it's easy to search. And reproducibility, it's very important because when you have a model who proves to be good, you want to be able to rebuild it in order to be able to iterate over it. And finally, it's teamwork, so you need tools to share the knowledge that you have when you run these experiments. So today, I'm not going to talk about all these solutions, which are great, but I call them monolithic because they provide you with all you need to do ML project, but it's not very easy to customize them. Instead, at Sicara, I think we are good Python developers. So instead, I propose to build an ML experiment tracking system with smaller bricks, which are DVC and Streamlit, and it will allow you to build a system that is fully customizable. So let's do machine learning. For the purpose of this talk, I will use this cats and dogs image classification problem. It's adapted from a Tensorflow tutorial. And basically, the goal is to build a model that, given an input image, says whether it's a cat or a dog. A few words about the dataset. It's available in Tensorflow dataset. It's 3,000 images. And here you can see some examples of cats and dogs. So how do we do this? We are going to build a training pipeline, which has 4 steps. The first step is to download the dataset. Then we have to prepare the dataset. We need to split the dataset in 3 parts: a train, validation, and test set. And then I need to train a model over the train and val sets. And finally, I need to evaluate this model so that I get a metric to know if it's working good. I'm going quickly over the script. Basically, it's adapted from the TensorFlow tutorial you can find online. So the train script, basically, what it does, it imports parameters. It loads the data. It defines a model here. And then it's trained here. The training, there is 2 steps during the training. First, the backbone is frozen, and then it's unfrozen. So let's say we want to run an experiment. So what do we need to do? First, we need to set up the experiment. So we need to define which model we want to use, on which data, define the parameters, and so on. And to do that, I can track whatever I do with using GitHub because it's code. Basically, it's code or it's configuration files that I can track with Git. So I'm happy with this step. Then I need to run the pipeline. To do that, I need to run the scripts in the right order, which is I'm not super happy with that because it's easy to mix up steps. And then I need to save the result because when I execute the training pipeline, it will produce files. For instance, the model weights, the metrics files, and so on. So I need to put it somewhere. And finally, I need to keep track of the experiment itself. Which model did they use, which parameters, which data, and so on. And I need tools to do this properly. So it's time to introduce DVC. DVC stands for Data Version Control. It's a Python library, so you can just pip install it. And what it does is that it allows you to track huge files that you don't want to version with Git because it's too heavy. And it will replace this huge file by small metadata files that you can track with Git. So it's very similar to Git LFS, for instance. And the API is very similar to Git. So if you know how to use Git, it's pretty much the same with DVC. Instead of git add your file, you just DVC add your file. And there is also remote data storage mechanism. So you can DVC push pull to save your results. What is really good with DVC, it's this reproducible pipeline feature. So in DVC, you can track the data, but you can also track the way you produce data. Say, for instance, here I have a 2-stage pipeline that will consume file A, B, C, and in the end will compute a file E. So all I need to do is to define the pipeline in a YAML file. I just define the 2 stages. To do that, I give the command, and I declare the dependencies and the output. And whenever I want to execute the pipeline, I just run DVC repro. And this will resolve the DAG so that it knows in which order to execute the stage. It will execute the stages, and it will track the input and output data with DVC. And there is also a caching mechanism so that whenever a stage, the dependencies of a stage didn't change, it will restore automatically the output. So that it speeds up a little bit the pipeline execution. So let's go back to our training pipeline. Just as before, we have 2 more files. Now I have a dvc.yaml file that, in which I define the 4 stages of my pipelines. And I have a parameter file where I define all the parameters from my training pipeline. And this parameter I directly injected in the pipeline definition, for instance, here, root dir, sub dir, and so on. So let's say I want to give a second try to run my experiment. So the first step, it's pretty much the same. But to modify the pipeline of parameters, I directly modify the dvc.yaml and params.yaml files. To run the pipeline, it's much more easy now. I just run dvc repro, and that's it. And to save the results, I have nothing to do because DVC will automatically track the output data. Now, regarding the experiment tracking, it's not very, I'm still not happy with that because whenever you execute a pipeline, it will create a metadata file that you can track with Git. So the experiment, it's tracked, you can access it with git log, but what you will get, it's only the commit names. And you see all commits in your project. You see experiment commits together with code commits, so it's not very convenient. The data is tracked, but it's not very easy to access. And another difference between classical software engineering is that when you do machine learning, it's not a linear workflow. When you do classical software engineering, it's mostly linear. You have branches, but when you code in your branch, you do one commit after the other, and it's linear. In data science, whenever you train a model, usually you train it with a lot of different hyperparameters, so it's not linear. In DVC, there is another feature which is called experiment that allows you to track experiment in a non-linear way. I will not enter into details, but what you need to see here is that it will create commits whenever you execute a pipeline, and it will track these commits, with custom Git references. And it's not linear. And since you have references for your experiment commits, you also have commands to access them. So let's say I want to see all the experiments from my repository. I can run this command, DVC explist, and it will give me something like that. So here you see this is the parent commit, and here you have all the experiments that derives from it. So now, if I want to access the details of these experiments, I just run dvc exp show, and I can provide the commit hash. Oh, sorry. So I need to copy first. Here it goes. And now I have the details of all the experiments that derive from this Git commit. So I have the metrics, the accuracy, I have all the parameters, and so on. So let's get back to running an experiment. And No, it's whenever I want to set up an experiment, I just create a new run of the pipeline by overriding some parameters. So instead of running DVC repro, I run DVC exp run, and I use this set params option to override whatever parameter I want to override. And there is a queue mechanism, so I can flush the queue and execute all the experiment in it by running DVC exp run all. And in the end, the output data will be automatically tracked by DVC. And regarding the experiment tracking, I can access all the experiment details by running DVC exp show. So it's much better now. Let's take a step back and let's have a look at the main experiment tracking system features. So with DVC, we are very good at logging experiment data and tracking the produced data. It's also very good for reproducibility, because whenever I want to rerun an experiment, I just have to check out the commit and run DVC repro, and it will re-execute the experiment the same way. Regarding the other features, comparing experiments, organizing experiments, and collaboration, I can do it in command line, but it's not very convenient. I could improve it with UI. So it's time to introduce Streamlit. Streamlit, as they say in their website, it's a faster way to build and share data apps. So it's a Python library. You can just pip install it and use it. And what it does is that it allows you to build an app without knowledge of how to build a web application. It's only Python, and it's very simple to understand how it works. So as you may have noticed, the slides I'm showing you are dynamic. It's because I made the slides with Streamlit. So let's have a quick demo. And in Streamlit, you can display whatever you want. So you can write text like that. So here you see the rendering. You can have more complex rendering, for instance, I don't know, LaTeX formula. You can render images like that. And you can render more complex data. For instance, let's say I have a data frame here. You just run st.dataframe, and it will show you this nice table. So it's very easy to show whatever data you want to show in your web app. And it's also easy to make interaction. For instance, let's say I want a slider. So here I define a slider between 0 and 100. And whenever I change the slider, you see here the chosen value gets updated to 35, and I write the result here, which is here. So whenever I change it, it gets updated here. So it's very easy to build interaction. And it allows you to build things like that. Let's say I want to investigate my model, and I want to see on which images the model is not sure. So the model, it outputs a probability between 0 and 1 of being a cat or a dog. 0 being it's a cat, and 1 it's a dog. So let's say I want to see images where the model is pretty sure it's a cat. So here I have such images. And let's say I want to see images where the model is not sure. so close to 50%. And here you can see there are 3 images that correspond to the slider values, and this one is interesting because there is a cat and a dog on the same image. So to build this Streamlit application in the right part, it's only a few lines of code that are here. So what I do is that I load the predictions from a CSV file. Then I define a slider with a double entry here. And finally, I get the 2 thresholds, and I use them to filter the prediction. And I use st.image to plot the corresponding images. So very easy to use. And I can do a lot more. For instance, I can directly test the model on whatever image I want. So for instance, here I have an upload widget. So let's say I want to try it on a cat. And here, the model says it's a cat, and it's pretty sure it's a cat, so it's working well. Now, let's say I want to try my model on edge cases. Let's take this one, for instance. So obviously, I don't have lion in neither the train nor the test set. And with Streamlit, it's very easy to build a UI to test a model on whatever image you want. So here, I get the image, and the model says, surprisingly, that it's pretty sure it's a dog. How do I do that? The code is a bit longer, but not that long. I have a function that loads the model with Tensorflow. I get the upload widget with st.fileUploader. I get the uploaded image in here. It's a pillow image. And if I uploaded a file, then I open the file and I pass it to the model and print the prediction. And that's it. So, what if now we combine strengths of both tools? On one hand, DVC is very good at tracking the data, but it does not provide any tool to build complex visualization. On the other hand, Streamlit is very good at building interactive web app on complex data visualization. So let's combine them to build something like that. So here it's a table of experiment application. Here you have a table with all experiments. It's very similar to what you get when you run DVC Exp show, but it's in Streamlit. So since it's in Streamlit, I can do whatever I want with it. For instance, I can sort the experiment by accuracy. And since this data is available, I can easily plot whatever I want. So this is the accuracy across experiments, but I can print the number of frozen epochs. And I can have more complex plots. So here, for instance, I plot the number of unfrozen epochs against the accuracy, but I can change dynamically this. So all this interface, it's the code is here. So it's a bit longer, but it's not that long. And the most important part in this code is these 3 lines, because they are the ones where I fetch the experiment information. So let's see how it works. First, I create a DVC repo in Python. It's very similar to the Git Python API. And then I retrieve all the experiment commits by running this experiments.ls. It's similar to DVC exp list command. but it's in Python. And what it gets you, it's this dictionary where you have the parent commit here and the list of experiments that derives from that commit. Now that I have this, I can run DVC exp show, but in Python, providing the references here. And what I will get is anything I need. Here I have the two parent commits, and for each of them, I have, for each experiment, the list of used parameters, the dependencies, the outputs, the metrics, and the experience name. So once I get that, it's very easy to build the table of experiment apps, because all I need to do is to use Streamlit to show the data the way I want. So here I retrieve the experiments metadata. I just flatten the data and put it in a data frame. I use AGGrid Streamlit library. AGGrid, it's originally a JavaScript library, and there is a Streamlit component that wraps it. And I show the table here, and after that, it's very easy to build the plots with Streamlit. Something else I could do is a diffing app. It's similar to when you code, you want to compare branches when you do a pull request, for instance, to see the difference between your code. Here it's the same, you want to compare two models. So let's say I want to see the images on which two models disagree. So here I have two selectors to select the experiment I want to compare. So let's say I take this one. Okay, it seems they agree. Okay, so this one is very interesting because, as you can see, the accuracy is the same, but there is two images on which the model disagree. So the true label are cats and dogs, and the first model is wrong on the first image, and the second model is wrong on the second image. And here I see the two images. So this is the code to build this diffing app. And what is important in here is the way I load the data, because to build, to know on which images the model disagree, I need to load the predictions that are tracked on different commits. So the predictions file, it's not on my current raw space, it's stored in another commit. So to do that, I use the DVC open function, which is very similar to the core open Python function, except that it takes a commit revision as an argument. And what it will do is that it will yield a file descriptor that you can use to do whatever you want. Here I just read the CSV file with pandas. So once I have this, it's very easy to build this, because all I need to do is to retrieve the two commits I selected from the select box here. This is the first commit revision. And then I load the prediction, providing the commit. And once I have the data frame, I simply can merge them and compute which images the both models disagree. And that's it. So, to sum up, if we take a step back, as I show you, Streamlit allows to build a very custom web application that allows you to compare experiments, organize your experiments, And it's also very convenient for collaboration because as a Streamlit, it's just Python script. You can just version them, you can share them across the team, and you can improve them during the project lifetime. So, to sum up, the main advantages of this approach is that you can do whatever you want with the UI. It's very customizable. You can make evolve the UI, and there is practically no limit to what you can do whenever Streamlit allows you to do it. And it's close to zero setup time because you just pip install DVC and Streamlit and you can go. There is no infrastructure behind it. You don't need Kubernetes or whatever. On the other hand, it requires that you have some software engineering skills because if in your team you have data scientists that are not comfortable with software engineering, it might not be a good idea. Probably a better idea to go with MLflow or framework like that. And since it's code, you have to maintain that code and to deal with technical debt. And the next step, here I just show you a few examples of Streamlit apps, but it's local. You have to start it locally, and the next step is to deploy them in a remote server so that anyone can access them, including non-technical team members. And there are many other tools that are provided with Streamlit and DVC. For instance, with DVC, you have CML, that stands for Continuous Machine Learning. It allows you to branch your pipeline execution with your CI/CD. So say whenever you push on some branches, it will automatically trigger a training or something like that. So that's it for me. Thank you for your attention. And you can find the code for the pipelines on the slides on this repo, and you can find me on Twitter or on GitHub. Thank you very much.
And for the questions, if you have any, Antoine will be out on the corridor receiving your questions. And thank you, Antoine, very much.
Thank you.